Gentleman up front here, but other than that, it's all cool. Let's see.
I think that's Will.
Well,
One of them is Will.
better hurry. Okay, so today and Thursday we're going to talk about GPU computing, or Gpgpu. I would say this is it's sort of a mix of slides. This is not necessarily the most streamlined, beautiful lecture that I'm going to give, but it is the part of the lecture that I actually probably know the best. So this is like my research field. So it's especially important that you ask questions in general if things are unclear or if there's things that you want to discuss. But pretty much what I'll do is today I'm going to talk about sort of ideas behind GPU computing and sort of what the big picture is, and then start talking about some fundamental algorithms and stuff. I'll talk about a little bit of sort of what people are working on Thursday, and then I'll speak a lot about NVIDIA's particular implementation of how they're doing GPU computing. So we're sort of getting some ideas today. How do we actually turn that into practice, and what does NVIDIA do in their hardware? Okay, so what we learned about on Thursday was about programmability. Okay, GPUs are becoming more and more programmable. We know that from the sort of graph that we've seen earlier, gosh, this is something that there's an enormous amount of compute power we can bring to bear on GPUs. And so what we're actually looking at here with the green and the red graphs is fragment processor power. Okay? How much fragment processor compute can you do? Okay? So that's a lot of compute. Okay? And it's an order of magnitude more than you can get even out of a quad-core Pentium. And so people are really interested in that. So the other nice thing is that besides being powerful, it's becoming more and more flexible. And we'll talk about that a little bit today. But we saw last time when we looked at like the early Vertex and Fragment program standards. And then how do those change as time goes on? Okay, well, suddenly we have the ability to do multiple texture fetches, and vertices got to do texture fetches. Then we started adding branching and looping kinds of things. The latest shader standards added integer computation. Previously, everything was in floating point and so on. Okay, so there's more and more we can do within every fragment or within every vertex, and then we can translate that to being able to do more interesting things on general purpose computation. Okay, so historically, this field has been Gpgpu. So it's general purpose programmability on graphics processor units. Historically, the way that people did Gpgpu was they did it using the graphics interface. So we'll talk about that today. So how do you draw vertices and rasterize fragments and so on and actually get it to do something that's not graphics at all? But it turns out that's an enormous pain for a number of reasons. And so what the latest hardware lets you do is sort of bypass the graphics pipeline and go access the compute units directly. And so this is a little bit of a marketing thing. NVIDIA has liked to move from here to here, because the common world kind of thinks of Gpgpu as, oh, it's this really complicated thing that involves doing graphics, and it's really, all these restrictions and so on. So they're sort of saying, scotch that one. We're not going to use that word anymore. We're going to have a new word, and that new word is GPU computing. Okay, so this is just a marketing thing. Either one of these is fine, but it's kind of taking off. So this usually refers to the graphics interface. That really smells good. Oh, man. No more lunch in here that smells that good. It's much better than what I had. But the cool kids today are calling it more GPU computing. So just so you guys know. Okay, so why do we want to use the GPU for this? Okay, well, one is the programmability, and there's lots of pieces in the GPU that are programmable, so that's really good. And what's really happened in the last couple of years is that we're able to program those GPUs with some high-level language. So when people did really early Gpgpu, that was something where you wrote everything in assembly. Okay, and we looked at sort of what the assembly instructions were last time. But then as time went on, the shading languages moved to things that were higher level, things like CG and HLSL. Okay? And now the compute languages are moving toward being able to do things in higher level languages. So you're not having to write things in assembly anymore. Now you can use something that looks a lot more like C or another language. Okay, the second thing that's interesting is that people generally want to do some sort of scientific-ish kind of computation, something that uses floating point. Throughout the whole pipeline now you get 32-bit floating point. Many applications, that's cool. Okay, 32-bit floating point is fine. One goal that GPU people have had is to use GPUs for more scientific computing kind of applications. People care about those a lot. And those are applications that often either require or the people think they require 64-bit double precision floating point. So the latest GPUs that have come out, both from NVIDIA and AMD, have 64-bit double precision support. So this raises a really interesting question for people that are actually building GPUs. Okay? And that question is, how do we support 64-bit? Okay? We make 99.99% of our money on games. All right? I'm a GPU manufacturer. I know that's where my money comes from. Games do not require 64-bit. Games are probably not going to require 64-bit anytime in the foreseeable future. There's just no point in having that for graphics. Okay? So then how do you go out and put, do you do this at all? And if you decide to do it, how do you do it? So what are some of our choices here? What might GPU people choose to do?
You split the computation into two 32-bit halves.
Okay. So one very sensible thing to do is, all right, well, we're going to build some really fast 32-bit pipelines. So can we figure out how to, gang two of them together and do 64-bit compute using a 32-bit pipeline? So it's more complicated to do that than with integers. With integers, there's just like carries that go across. With floating point, it's a much more complicated standard, and so like to do multiplies is a lot tougher. But that's actually what I would have expected that they would have done. Okay, if I was building the GPU, I probably would have tried to figure out how you can take a 32-bit floating point processor and how to make it run 4 times as slow, but make it work as a 64-bit processor. You could emulate it. Okay. And so there's been a lot of very interesting research in mixed precision kind of arithmetic where, well, you do most of the stuff in 32-bit as much as you can, and then only the really important parts you do in 64-bit. How do you figure out what the important parts are? Okay, that's an interesting research question. That's sort of this mixed precision work. So that's something else that you can do. What NVIDIA did, at least, and you can ask the architects when they come here, is they put on a separate 64-bit unit. But they didn't put on as many of those units as they had floating point units. So they just put on a few. So as a result, this 64-bit is much less compute bandwidth than you see as 32-bit. But this is going to be an ongoing challenge going forward, right? Because this is only useful for GPU computing. So when the NVIDIA guys describe it is they say, well, when we're trying to decide to put something new on the chip, okay, we know that we're going to put on this extra feature, and it's going to cost us an extra square millimeter of die area. Okay, it's going to take more hardware to be able to support 64-bit. Okay, we ship a million. Okay, so that extra die, that extra square millimeter is going to cost us $3 more per chip. Okay, we ship 1 million GPUs a week. So if we put on 64 bits, we know that we have to make $3 million of extra revenue per week for this to make sense. Okay, that's a really nice way to put it. Okay, I would say right now there's no chance that this is going to make money in the near future. Okay, because they really do have to make an extra $3 million a week, and they're just not selling that many only to do compute. Okay, but they're doing it as an investment going forward. They're saying, well, if we get people using it now, maybe 5 years from now, people are going to buy lots of them, and they need to start being able to use it today. Okay, but right now, not making money.
So how much of GPU computing influences the next hardware design for say NVIDIA GPUs? Because clearly this is something that only GPU computing uses.
Yes.
But they still make most of their money from video games, so
pretty much all their money.
Yeah. So how much, what's the point of something, say, like CUDA or something, if it's not really making them that much money?
So, I mean, that's the million-dollar question, right? This is exactly what you should be asking the architects when you come. Why are you doing this? This can't possibly make economic sense today. Which is true. And for me, at least, the answer is, well, it could make economic sense tomorrow. Okay, so if you're NVIDIA, what you're afraid of is that the CPU will swallow up the GPU. Okay, you're afraid that, okay, well, the CPU can do more and more. They're going to put graphics capability on the CPU. Eventually, they're going to make us obsolete. Why would somebody buy this when it's good enough for 98% of the people to do it here? So their goal is to aggressively go after this issue of, hey, we are going to try to take work away from the CPU. We're going to try to be good processors for things today that the CPU does. If they can do that, then that's obviously a benefit to them. And so this is sort of an initial salvo in that direction that they're trying to do. They're trying to grab things that weren't traditionally theirs, expand the area of what the GPU can do. At least that's how it makes sense for me. This is exactly what you should be asking our industrial visitors. Why does this make sense? Does that answer your question?
Yes.
Okay. So, all right. So what we're trying to do here is find things that, the kind of problems that might run well on GPUs. Okay? So we know GPUs have a lot of compute power, but we know they have a restricted programming model. Right? We couldn't boot an operating system on a GPU. Okay? Or if we could, it would be so slow as to be totally unusable. So what are the applications that are well suited for the kind of processing that the GPU could do if we use it as a more general processor? And that's sort of what we're talking about today. What sort of things can the GPU do well, and how does it do those things? Okay, so what's hard? All right. Well, the first is this issue of video games. Right? This is why we buy GPUs right now. So it has a programming model that's historically completely done in terms of graphics. Right? That is the programming model. You program OpenGL. Right? That's your programming model. So what's opened up more recently is programming models that are not wedded to the graphics pipeline quite so tightly. But these things are still, kind of restrictive, and the processor was built essentially to do graphics. Now, these architectures are very parallel. Okay? With CPUs, everybody's telling you, oh, go to multi-core, you got to do threaded programming and so on. But if you write a program that's not threaded, it's still probably going to work pretty well. Most programs aren't threaded. Most of what you use isn't threaded very much. It's still going to work. If you write a serial program with a GPU, you have no hope of success at all. Okay? So it's a programming model from the outset that has to be parallel. You have to be thinking of writing things with thousands or tens of thousands or millions of threads at a time. If you don't do that, you're dead. And if your problem doesn't lend itself well to something that is very parallel, then it's just a bad match. So what Dave Libke from NVIDIA always says is GPUs don't even get out of bed for fewer than 1,000 threads. Okay, if you can't take your work and get at least 1,000 threads of things to do, don't even bother. It's not even worth it. Okay, so that's an issue. Another thing is it's very different in terms of the evolution of a GPU compared to the CPU. Right? What does your CPU do today that it couldn't do 20 years ago? Okay, not much, right? Maybe you move some memory controllers onto it. It's got a little bit of parallelism like SSE or MMX that it didn't have 20 years ago. Okay, but basically it's running the same instruction set it did 20 years ago. Okay, things don't really change very much, and so when you write a program, it's good for a long time. Okay, and that's part of why the CPU is very successful. But GPUs evolve all the time. Every year there's new stuff coming out. Okay, you don't, if you're a CPU programmer, you don't watch the trade journals for this is going to be in the next CPU. Like how do I use these new instructions and these new capabilities? Whereas the GPU, you're doing that every 6 months. Okay, so things are changing very quickly. It's also largely secret. They don't really tell you what's happening under the hood. Okay, so as an example, GPUs have a texture cache. So we go out to memory, we grab some texture to do our rendering. There's a cache there. What do we know about that cache? Nothing. We don't know anything at all because they don't tell you. They don't tell you how big it is. They don't tell you how associative it is. Things that would help you as a programmer, okay, but aren't really going to help you as but they're not going to tell you, right? Intel will be very open about that stuff with its CPUs. They'll tell you exactly how everything works so that you can optimize for it. But the GPU manufacturers, because of this, don't tell you. What they don't want you to do is to optimize for this one particular cache organization, and then they're going to totally change it in the next generation, and your code's going to be horrible. So it's better for them to say, you know what, we're not going to tell you the low-level details, and then you're not going to optimize for the low-level details, and we're free to change them under the hood. That's the philosophy that they've taken. So part of your assignment is doing a little reverse engineering. There's lots of things that the GPU people don't tell you that you can figure out through some experimentation. So a lot of the historic Gpgpu kind of work is reverse engineering the way things work so that you can make it work at all.
It was kind of hypocritical because it seems like they don't want you to optimize for their GPU, but they will optimize for a specific path on a specific video game?
Well, it's the golden rule, right? He who has the gold makes the rules. So, I mean, it's their GPU. They get to do whatever they want. They would say, and I think accurately, that they're doing it for your protection. That they make substantial changes from generation to generation. And changes such that if you optimized for one, it really would be a poorly suited for the next generation. And so if you optimize to that level, you're kind of out of luck. Like you as a customer would be very upset. So they'll tell you the things that they feel will be constant for a long time, but they will deliberately not tell you the things that they're still figuring out underneath the hood. So I don't blame them for doing that. But as a researcher, it's very desirable to know how these things work. So there's always some tension. I feel like in general, we get to know the things we really need to know, and the things that they won't tell us, we can largely figure out if we have to.
Do you think the instruction set will start stabilizing after a few years? Like they kind of know where they're going, and that's going to be the set standard, and it'll be like that for at least 5 or 6 years or something like that?
So that's a great question, too. So the instruction set, right? Is the instruction set going to change? So we saw like the Vertex and Fragment program instruction sets, and we know those have been migrating quickly. Those have been changing quickly. They've been adding things. They've been changing the way things work and so on. So at least with NVIDIA's compute stuff, the way that they're doing that is they are not really telling you about the underlying instruction set. So one of the projects that somebody did a couple of years in here is Eric, in our research group, totally reverse engineered the instruction set. So he went in and like played with some bits and ran programs and figured out what it did. It was a very cool project. What NVIDIA's decided to do is they have an assembly language. And they'll tell you about the assembly language. And NVIDIA's assembly language is called PTX. I don't even know what it stands for. But then they can change the instruction set underneath the assembly, but never change the assembly. And they've said, we're going to keep this assembly for a long time. So again, that's another example of they're not going to tell you what's underneath, but they're doing it for your own good because they're going to change what's underneath. So I think they'll keep changing the instruction set, but they'll keep the assembly pretty stable. OK. So GPUs aren't good at everything. Okay? There's things you as the programmer would love to be able to have that just aren't there. And that's very frustrating for programmers. One of the nice things is that the sort of things that you wish you had are coming. Okay? So for a long time, this 64-bit thing made people walk out of the room. Okay? Oh, no double precision, I'm totally out of here. Okay, now I can say, well, there's GPUs that are doing these things. We didn't have integer computation for a long time, and people went through some amazing gymnastics figuring out how to use floats as integers. Okay, now we have integers. Didn't have that for long. Indexed write, scatter. We're going to talk about that today. Another feature that's new as of, I guess, 2 years ago. Let's see, atomics. Okay, the ability to do atomic operations. That's something new as of like a year ago. So these are new features that are sort of coming in. So that's a good thing. It's still not like running a CPU, okay, and it's deliberate. We don't want to have a whole bunch of CPUs. We want to have this chicken versus oxen thing. We're still building chickens, okay? We're not building oxen, okay? But the chickens are becoming more capable. Okay, so I'm going to talk about one particular programming model starting out, and this sort of motivates how do we take a programming model and map it to a machine. Okay, so the programming model is sort of what's the programmer's view of the machine. Okay, and then there's a machine model underneath that that says, you know, sort of how the machine actually behaves. So what I'm going to talk about is a programming model called the stream programming model. And a lot of early Gpgpu work used this kind of programming model, and I'm sort of motivating it by talking about what sort of modern chips look like and how much they cost and what the issues are. So we've got this giant chip here, right? This is a big chip. And roughly, a 64-bit floating point takes up the little red box in the corner. Okay? Today, you can put hundreds, probably thousands of floating point units on a chip. No problem at all. Thousands easily today. Okay? You've got billion transistor chips. No problem to put thousands of processors on there. So the issue today is less how do you put a lot of computation on the chip, and it's more how do you put computation on the chip in such a way that you can actually get to the computation. Okay? You can actually take advantage of all the processors on the chip. So if I just gave you 1,000 floating point things on a chip and said go, okay, that's really hard to program. Okay? So what we want to do is we want to have hardware that matches a programming model such that we can really take advantage of all these floating point units that might be on a chip. Okay. So we want to exploit all the computation that's on the chip. The other thing we're really worried about is computation, or communication. So when I started being a student, people didn't worry so much about wire delays. Right? The amount of time it took to do compute was much longer than the amount of time it took to communicate. Okay, and that's because my first computer ran at 20 megahertz. Right? It seems silly to all you guys, but that was my first computer. 20 megahertz, that's a long time. It's 50 nanosecond clock time. Right? So it's easy to send a signal from one side of the chip to the other side of the chip in 50 nanoseconds. Okay? Piece of cake. Today that's not true anymore. Okay? Today we're running at 2 and 3 gigahertz. It turns out that it actually takes multiple clocks to go across a chip now. Okay? And that's expensive. And the communication is much more important today than it was many years ago. And so whatever we design, we have to have a programming model that lends itself well to efficient communication. If all of our communication goes all the way across the chip every clock cycle, we're not going to be very fast. And so communication is also very important. Right? Computation gets better every year, but the speed of light doesn't change. So this is something that's more and more important going on. Okay? It's all about the communication rather than the computation. So the programming model I'm going to talk about is a stream programming model. And our goal is, well, we have these realities as far as VLSI goes, as far as the way we build chips today. Okay, we'd like a software programming model that matches those hardware realities. So I'm going to have a couple terms here that are very important in terms of Gpgpu. One of them is streams, and one of them is kernels. Streams is how we express our data. Kernels is how we compute on that data. Okay, and we're definitely going to see this word kernel again. So the idea here is that in the stream programming model, all of our operations are on streams of data. They aren't on individual pieces of data within a stream. Instead, they're on streams of data. And what's a stream? A stream is a bunch of data records, all of the same data type. You might have a stream of floats, or a stream of ints, or a stream of triangles, or a stream of pixels. Okay? And all of the data that you have is expressed in streams. And when you operate not just on one element, you operate on a whole stream of elements. So I don't say I want to rasterize a triangle. I want to say I want to rasterize a stream of triangles, and I want to generate a stream of fragments as output. Okay? So how do we actually operate on things? We do those with kernels. Okay? So kernels have inputs and outputs, but the inputs and outputs are streams of data. So we might have two streams coming into a kernel that processes the data and produces an output stream. You can also chain kernels together to do more complicated kinds of operations. So graphics actually works very nicely in this. Right? You can totally think of graphics in the stream processing model. Okay? You have a stream of vertices coming in. You run it through the Vertex program. You get a stream of processed vertices coming out. Okay? You do triangle assembly. You have vertices going in and triangles coming out. Right? You do clipping. Triangles coming in, different set of triangles going out. Rasterization has triangles going in, fragments going out. Fragment programs have fragments coming in and fragments going out, and so on. Right? And it's very much a stream model because we know that it's not efficient just to work on one thing at once. We actually want to work on whole streams at once. Okay? So this is kind of an elegant way to express things. So we had these things we were interested in, ample computation and efficient communication. Okay? This is why the stream programming model is well suited to this. So the really important thing is that streams expose parallelism. So one of the hard parts about programming in parallel is you have to totally change your code up, and you have to think about doing all these things at once. Well, the nice thing is if I say, well, I want to operate on this stream of triangles. Okay? The nice part about a stream is it's sort of inherently a parallel structure. I've got all these triangles in the stream. I can process each one of those in parallel at the same time. Okay, and in general, I structure my computation that way so that the elements in the stream are independent elements. And when I process a stream, usually what I'm going to do is I'm going to process every element in that stream. And so much of that processing I can do in parallel. Okay, and that's really key. I've got all these computation units. I better try to keep them busy. I better try to process them in parallel. I can also think about having pipeline parallelism, this task parallelism. And we know we have this in our graphics pipeline. We do sort of this space multiplex kind of approach. Okay? our task parallel kind of approach where we have lots of different things happening at once. You can do the same thing in the stream programming model, right? You have a bunch of kernels that are sequenced up. So this kernel's doing the first part, this part's doing the second part, and so on. So that's good. And then when you concentrate all of your arithmetic into a kernel, this gives you what we call high arithmetic intensity. You don't want to communicate all the time with global memory. Instead, in the stream programming model, you sort of bring in all the data that you need as far as streams go, and you do all your computation locally as much as you can. Try to keep things as close to the processor as you can. So you're not always going out to main memory. Okay, so one consequence of the stream programming model is that it has a different kind of locality than we're used to. So usually in a CPU, we deal with locality in terms of caches. And caches are really good at capturing temporal locality, okay, that once we see something, we'll see it again soon. And spatial locality, that once we see something, we'll probably see its neighbors too. Okay, so this is hopefully something you got out of your computer architecture class. Now, the kind of locality we see in stream programs are a little bit different. Okay? One thing you never get is temporal locality, because you're reading everything once as part of a stream, you process it, and you write it once. And then you read it once, and then you process it, and you write something different back. Okay? Pretty much for every element, you read it once and write it once, and that's it. You never see it again. And that's totally true in graphics. Once you finish processing a triangle, you never process it again. Right? You're done. It becomes pixels. It's done. So having traditional caches doesn't make a lot of sense in a stream program. Okay? Instead, we have what we call producer-consumer locality, that you produce a bunch of data results, and then you immediately consume them. Okay? So you sort of write once, read once. And you really want hardware to take advantage of that. Okay? So that's one of your goals. It's a different kind of locality than we often see in scalar kind of programs. Okay. The other thing that's nice about stream programs is that their memory accesses are usually very predictable. So when you know that you're not just reading a single element, but you're reading a whole stream of elements, you have a pretty good idea what those memory locations are going to be. And it's probably going to be reading this nice, long strip of things. Okay, so that's really good. And so when you deal with entire streams at once, your goal is to really optimize for the throughput of the entire stream as opposed to the throughput, to the latency of any individual element. So this idea here about latency hiding is very key to both the stream processing model and the and graphics programs in general. Right? You're very much willing to trade off the latency of any individual item for the throughput of all the items. So if you're in a CPU, okay, you're building a CPU, and you have your operating system thread run, okay, and you decide, I want to run that faster. Okay? What sort of things have people done in hardware to run that faster? Okay, what are some of the hardware techniques you use to make a single thread run faster?
Branch prediction?
Okay, branch prediction. All right, so you put on all this branch prediction hardware so that you're not waiting for the result of a branch. Great. What else?
Pipelining.
Pipelining. Okay. How does pipelining help one individual thing go faster?
The instructions that are coming in can not hold up the ones that are behind it.
And I would say that's more for that.
Yeah.
Okay, so pipelining, I would say, is more of a throughput-oriented thing than a latency-oriented thing. Okay.
Out of order execution.
Okay, out of order execution, right? I've got all these instructions coming in. It turns out one's blocked for some reason. I'm waiting to come back from memory. So, but can I run some other ones past that don't depend on it? Okay, so what do CPUs do? CPUs have all this hardware to do branch prediction and out of order. How about in the memory system?
Oh, I was going to say prefetching.
Okay, prefetching. Okay, let's go get our data early. Okay, what else in the memory system? Caches, great. Easy answer, totally the right answer. We have all these cache hierarchy in here. The whole goal is to make it so that we can get something back fast. Okay, so that's what a CPU is totally built around. Okay, GPUs and stream processing systems really take a different approach. So they say, we're going to build this really simple processor. And the simple processor isn't going to have any of this cool stuff like out-of-order execution or branch prediction or prefetching. Okay? It's just going to do simple things. And so it's going to stall a lot. Okay? Because we built it simple, there's going to be lots of times when we're waiting for something to come back from memory, or we're waiting for a hazard to be resolved. Lots of things that are going to make us stop. So what a CPU would do is try to solve that problem. Okay, well, it's waiting for this particular reason. I'm going to put in hardware to solve that. A GPU is different. A GPU is going to say, okay, you're running this thread. It stops for some reason. Okay, we're just going to start running another thread. Okay, so I'm running a thread. I have to go out to main memory. Okay, I'll send out a request to main memory, and my processor will switch to doing something else. And then we'll run that until it stops, and maybe I'm back by then. Or maybe I'm not. Maybe I have to start running my third thread, and I start running this. Okay? And so whenever it stalls for any reason, if you can give it enough work to do, it can always switch to something else and start running that instead. Okay? So the goal here, the phrase that we use, is latency hiding. Okay? Some things take a long time. It takes a long time to go to main memory. It's going to take you hundreds of cycles to go to main memory. So once you kick off something to main memory, it's fine if it takes hundreds of cycles, as long as you have something else to be doing in the meantime. Okay? This is absolutely fundamental to the way that GPUs are built today. If you look at the traditional graphics pipeline, it's going to get down to doing fragment processing. There are going to be thousands of fragments that are in flight at the same time. They're all in the middle of their processing in a modern GPU. They're all running. Most of them are waiting for something. But if you have enough fragment work to do, you can always keep your processor busy. So any individual fragment is going to take a long time to finish because it's waiting a lot of time. It doesn't have any hardware to catch up with that. And maybe when it's done waiting, somebody else is running in its place. So it's going to take you a long time to run any individual element. But your throughput is really good because you're going to have lots of parallelism. And each of those processors is going to be busy all the time. They might not be working on the same thing all the time. They might be working on a bunch of fragments at once. Okay? But your throughput is going to be really good. So CPUs use all these hardware structures to minimize latency. GPUs say, we're not going to do that. Instead, we're going to have lots of processors, and we're going to use latency hiding to try to alleviate that problem. Yeah?
About the producer-consumer locality, can the producer be the consumer? Can you have feedback?
Yes. And the question, so what sort of things would you think would be neat for feedback?
Well, like AI applications, if you were to do that in CUDA.
So, yeah, so there's issues with hazards. Do you read, whenever you have feedback, there's an issue going on there. Usually, probably what's going to happen is you're going to have sort of this ping-pong structure where, this guy runs through a kernel, generates some output. Then that output will be treated as the input and sort of go through the kernel again. So it's going to sort of make this zigzag down. To some degree, that's feedback. It really depends on your system, how that's actually implemented. But that's legitimate. But the phrase people usually use there is double buffering, that you're ping pong between the two buffers. And that usually lets you do some sort of recursive structure or some sort of feedback structure like that. OK. So I'll start talking a little bit about how this starts to map to the GPU. All right. So we take this stream idea here. And we think of a data array as that we're processing, and we treat that as a big chunk of memory. Okay, so remember what a stream is. A stream is a bunch of things of the same data type. Okay, we express that in the graphics context as a big texture, okay, or a big buffer of input data. Okay, let's say we're processing one color, or we have a stream of colors. Okay, well, texture is really nice because each of these elements is a color. But you know that we can make textures out of anything. We can have textures of just a floating point value. We can have textures where each one of these is a triangle if we want to. Okay, the important thing is there's lots of them, and textures are good for capturing lots of stuff. And then when we deal with one of these elements, okay, we do like a memory read from the stream, then we think of that as one sample of the texture. So we've sampled this texture. And if we want to process the entire stream, then what we're going to do is do a sample for every element in this texture. OK. So now we sort of learn about this, and we say, OK, what's the GPU going to be good at? Okay, based on the way that it's built, based on the way that it's built with this throughput-oriented idea. Okay, so graphics is good for the stream programming model. Graphics is good at stream hardware kind of organization. And the GPU you can think of as a big commodity stream processor. Hey, that's exciting. So we want to take these streaming kind of ideas, these graphics kind of ideas, and apply them to other things. And so the things that we care about, okay, are things that need a lot of computation because GPUs can give you a lot of computation. Okay, We care about things that have regular computation. If you want to do a stream program and you want to do something different for every element in the stream, that's not usually going to be a good fit. What you're going to be good at is when you do computation where you're doing similar things to everything in the stream. Okay? Because then you can get nice regular parallelism out of it. Okay? So, what we'll be talking about for sort of the rest of today and certainly Thursday is what are some of these tasks and how do we map them to the GPU and how do we try to make them more regular? How do we extract parallelism from them? Okay. So, this is a very big picture slide on how we actually structure a GPU program. Okay, so everybody says, all right, kind of get your big picture here, but then I actually want to write a GPU program. How does that work? How do I actually use the GPU? Okay, so the first thing is that the GPU is kind of the dumb guy in this loop. Okay, the CPU is sort of doing all the smart things, and the GPU just does the heavy computation lifting. So the CPU says, all right, I want to run this particular application. Here's the input. So I'm going to calculate some input data. Okay? So the CPU is responsible for that. The CPU takes this big wad of input data and says, okay, now I need some computation done on it, and I want the GPU to do that computation. The CPU will make a call to take that data and move it over to the GPU. Okay? So usually this is a copy over the PCI Express bus. Okay. Then the GPU will take that data and it will land in what we call GPU main memory. So high-end GPUs today have their own memory system, right? The CPU has its own memory. The GPU has its own memory. So it's going to go into the GPU main memory that's implemented in DRAM. And then the GPU will call a number of kernels on it, okay, however many the program requires it to do. They'll actually be sequenced by the CPU. The CPU will say, call this kernel, call this kernel, call this kernel. Now, each kernel is doing a lot of work, so that's okay. I mean, it's not like this microcontrol. It's expected that you will kick off a kernel and it's going to take a very long time to execute, okay? Hundreds of thousands of cycles. That's fine. So it's going to run out of GPU main memory. The GPU doesn't get to go back to CPU memory at all. Okay? The GPU is running on data only that's in its main memory. Then when it's done, it's going to produce some output in GPU main memory, and the CPU is going to say, okay, now you're done. Now we're going to copy this back to the CPU. Okay? And the CPU can do whatever we want. So let's say we want to write an efficient GPU program. Okay? What are some of the lessons we draw from this? Okay, if we want to write something that's efficient, what characteristics do our GPU programs need to have?
They shouldn't be accessing external memory, whatever they have.
Okay, so one thing is you certainly have to write a GPU program that only runs from within its own GPU memory, right? Because GPU doesn't get to go reach into CPU memory and get data. So you definitely have to send everything you need to over to the GPU. Okay? What other things? There's sort of an important lesson. There's a lot of stuff going on here. It's a lot of bookkeeping. Okay? And kind of the important lesson is the GPU better be doing a lot of work. Okay? If the CPU goes to all this effort and it sends all this data over and it has to initiate these transfers and so on, and all your GPU is doing is 2 plus 2 and sending back the result, it's probably not a good use of the GPU. Okay? What you really want is the GPU to send over some data and to do a lot of work on that data. And then when you're done, you send it back to amortize the cost of this startup and transfer kind of thing.
In the case, we need to duplicate the same data in both memory, in the system memory and the GPU memory. So this is kind of a memory inefficiency.
That's potentially true. So, but is that any different than, so we're running a CPU kernel here, and we have something in main memory, and we run it through a kernel, and then we produce this, and then we run it through a kernel, and so on. And we take this kernel and we copy it over here to the GPU and bring it back. Okay, is that really any different, though? I mean, yes, these two things are existing at the same time, but once you transfer this over, you can erase this. Okay, once you transfer this back, you can erase this. It's not horrible. I mean, yes, it's true that it isn't. I mean, the copy is not an efficient thing. Okay, you'd prefer not to have to do that copy. And part of the problem is that copy goes over this PCI Express bus and it's not very fast. So you want to minimize that. What you want to talk about is sort of the ratio between how much transfer do you have to do compared to how much compute you actually do when you're over there. And you want a lot more compute than transfer.
So it seems like the applications you'd want to port stuff from the CPU to GPU, it'd be more streaming type stuff. So if you're streaming, like if it's really what you're thinking of, then there really is no overhead because it's more a flow of data going to the GPU and then coming back.
So that presupposes that you're able to do a lot of overlap in terms of communication and computation. Okay? And that's not quite there yet. It's getting there. So in the streaming model, can you keep up your throughput by doing that? You hope so. And that's certainly your goal. But you'd really like to be able to have overlap of both communication, both directions, as well as computation to be able to make that work. Okay? But yeah, that's exactly what you'd like to be able to do. If you're using it as a coprocessor, though, and you care about like latency, oh, I need to get this job done. How quickly can I get it done? Well, I mean, there are costs associated. It takes time to send it over there, and it takes time to bring it back. So you'd better do a lot of work that sort of eliminates that. I mean, you're at a disadvantage when you start because you've paid all this time. So you better be a lot faster so that you can make that up. Okay. Yeah?
I just had a generic question. I mean, this is the thing a couple of years ago when they had the macro processor, right? That was a separate one.
Mm-hmm.
Or the CPU manufacturers try to grab the graphics up in there.
So, I mean, like, so which math coprocessor are you speaking of?
These is with 386 ones, right? I mean, between the 386 and the 486 data.
Sure. So you could buy a 387.
Yeah.
Okay. So if you look at kind of the history of building a coprocessor, it's that you build a coprocessor. So first you figure out how to do something cool, and you do it all in software. And then you say, boy, that's not as fast as I'd like. I'm going to build some special purpose hardware and use it as a coprocessor. Okay, so I'm going to build floating point hardware. And then it's on 2 chips. And then you say, okay, well, that turned out to be pretty useful. I'm going to fold it back onto the CPU. That's exactly what happened with a floating point coprocessor. So the question is, will that happen to the GPU? Okay? And I had this conversation in my office hours. I think that has to do at least as much with economics and market forces and so on as it does with technology. So it's certainly possible, technically possible, that the final fate of the GPU is going to be part of the CPU. It's possible that the final fate is going to be part of the chipset. And it's possible that it'll continue to be discrete. So what is a little different about the GPU than some previous coprocessors is everybody today has an interface that depends on doing 3D graphics, right? This requires a 3D graphics chip to run the user interface. Vista has Aeroglass. Okay? 3D graphics are part of the way that we do a lot of our communication now, and people need high-performance graphics to make those things work. So the video functionality isn't going away. The problem for somebody like NVIDIA is keeping ahead of the guys that are doing the cheapest possible thing and are doing it just good enough. And that's a really hard business problem. So, right, it's a little bit of an offshoot, but it's a good question, right? Is this going to continue to be the case? Okay, so you could certainly see like people saying, this copy is just really inefficient. Can we get faster buses? Or do we need to bring this closer to the processor? Okay, so we are going to see faster buses, but we are going to see people bringing it closer to the processor. AMD's AMD will have a product that they call Fusion internally, and the first incarnation is called, I think, Jaguar. And it'll be a CPU and a GPU on the same die. Okay, so they build a couple CPU cores. They have a GPU core. They put them in the same chip with the same, right? So that's really fast. You can communicate between those very quickly. So it'll be interesting to talk to the AMD, to Justin when he comes up. You know, how is that going for you? But I don't think they've really announced anything yet. Okay, but people will take different approaches architecturally to making this work. Okay, so what I'm going to go through is sort of how we program a GPU for graphics. Okay, sorry, this is a very important slide because I want to make sure people understand how we're using the GPU for compute. And it doesn't seem like rocket science, but this is something a lot of people get wrong. So how do we program a GPU for graphics? And then I'll talk about how we program a GPU for doing general purpose stuff, and I'll talk about that in 2 different ways. Okay, so this is sort of all computer graphics in one slide. What we actually do, what we do is we specify a bunch of geometry, and then we rasterize that geometry. What it's going to do is create a bunch of fragments, and each of those fragments we're going to shade with some sort of program. Okay, our fragment program, SIMD program. We learn how those things work. Okay, here I'm saying it's a SIMD program that we're going to run the same program on all those fragments. Okay, different data, same program. Okay, what can we do in that program? We can go out to texture memory and get texels from texture memory and use that in the shading computation. Okay, we know that. And then when we're done, we can take that final image that we produce, and we can say, okay, we'll treat that as texture on a future pass. Haven't really talked about that in class, but it's very common in today's games. It's a technique called Multipass, where to generate one final image, you'll actually run through the graphics hardware multiple times. Okay, so for example, a modern game will do a pass just to compute shadows, and then use that shadow calculation in a graphics pass to actually draw things that look like shadows. Okay, that's pretty cool. Everybody clear on this? This is all computer graphics, one slide. Okay, so when we did old school Gpgpu, this is the way that it would work. All right, we're going to draw a quad that's the size of a screen. Right, I want to draw a 1,000 by 1,000 rectangle. What that's going to do is it's going to generate a SIMD program over every fragment. Okay, but the way I want you to think about this is that what we've essentially done is launched 1 million threads. Okay, let me say that again because it's important. We have a 1,000 by 1,000 grid here. When we, or 1,000 by 1,000 pixel rectangle, when we send that through the rasterizer, it will create 1 million fragments. Right? 1,000 by 1,000. That's 1 million fragments. I want you to think about that as launching 1 million threads. Okay? We've built a massively multi-threaded program this way. Okay? Each one of these threads is going to be processed by a different SIMD program, just like in the graphics case. Okay? We can go to texture memory and get arbitrary data out of global memory. Okay? And the phrase we use to describe fetching from global memory, that we have a lot of things that are going to memory anywhere in memory, is gather. Okay? That what we do is we go gather the values we need from global memory. Gather is usually used in terms of vector computation, where you have a lot of items, each of which are going out to random places in memory. Okay? So that's the word we mean when we say gather. We also talk about scatter. So gather is a read operation. Scatter is a write operation, where we go to global memory, a bunch of guys go to global memory, and they'll write to arbitrary places. Okay? But here we're just talking about read-only stuff. Okay? So then, let's say we're doing a fluid simulation. All right? We have a pool. We want to model a pool of water, and we drop a rock in the corner, and we want to see how the waves go. All right? So how am I going to express that here? Well, what I want to do is take that pool that I have and say I'm going to model that as a 1,000 by 1,000 mesh, and I'm going to model the water behavior at each point of that mesh. Okay? At each fragment that I generate, I'm going to model that. And so this guy here, what his program is going to look like is he's going to go look at the values of all of his neighbors on the previous time step. Okay? He's going to gather those values. He's going to use that to compute his next state, and then write back the next state, but write it back as a picture. Well, it's not really a picture. Okay? It's treated like a picture, but it's really a floating point value that indicates how high his water is, what's the elevation of his water, or how deep that water is. Okay? And then everybody computes the next time step, and then you run this whole thing again on the next time step, and you use the values from the previous time step, and so on. Okay? So that's the way that Gpgpu used to be done. And it was really hard because you're doing fluid simulation, but you are writing a graphics program. You're writing a graphics program that does texture fetches and rasterizes a 1,000 by 1,000 grid and all these things that have nothing to do with the problem that you're trying to do, but look like graphics. Okay, look like graphics, but actually compute something else. Okay, we sort of clear about how this works? Any questions about how this worked? Okay, it was kludgy and it was hard because we're doing computation that has nothing to do with graphics in the graphics interface. So when people talk about Gpgpu, or NVIDIA talks about Gpgpu as a marketing term, this is sort of what they're talking about. This is complicated. And so some smart folks said, all right, it seems kind of silly. We've got all these nice compute units. Why do we have to go through the graphics interface at all? Why do I have to worry about, sending this, rasterizing, worry about the rasterizer, or worry about having to specify vertices? And let's just let people talk directly to the compute units. Okay? That's sort of where we are now. This is more of our GPU computing kind of idea. Okay? And so again, it's going to be the same steps. The same thing's going to happen in the hardware. But now we can use a vocabulary and use programming languages that are much better suited for this. So now instead of talking about rasterizing a giant quad, we say we're going to define a computation domain over all the elements. We're going to define a stream, essentially. Okay? We're going to define a stream that's, in this case, a two-dimensional stream that's 1,000 by 1,000. So we just declare that. Okay, and then the system has to figure out, well, what he really means is launching 1,000 by 1,000. All right. So, but you just get to say, I'm just going to run this domain, and the hardware and the software figure out how to partition that. Okay. Then we say we define this domain. We're going to run a kernel over that stream, and we're going to launch a thread for each element of that stream. Okay. And that thread will run a program, and that program is going to run over all the elements of the stream. And that program will be SIMD, SPIMD, some sort of flavor of that. The new hardware lets you, at each one of these programs, you can both read from an arbitrary place in memory or write to an arbitrary place in memory. Okay, and that's really handy. It's nice to be able to write to memory in a structured way, in a random way, and there's a lot of algorithms that depend on that. Okay, so scatter is kind of a neat thing. And then we can take the result here, and we can say, well, we'd like to use that for more compute, or it turns out we created a result that was actually a picture, and we want to use that as texture. So you can take the result and say, okay, this is texture. Now we're going to go out of the general purpose interface into the graphics interface and use the result that we just had. Okay, questions about this?
How do data dependencies work out? Because if, say, one pixel stalls for some reason or the other, and he's dependent on the previous frame's pixels, he can kind of think of it. And so doesn't that, I'm trying to think, well, there's some data dependencies there. It seems like if you have two buffers, that you can't really move one buffer unless everyone's finished with that buffer, and then you can switch. And it seems like that'd be I don't know.
So this is a great question. Okay, and the question is, how do we deal with data dependencies? And so there's sort of two levels of data dependencies that we're talking about. Okay, and one level is going to be very finely dependent on each other. So if we look at this and this, can we make this guy's pixel depend on this guy's computation? Okay, does that make sense from a hardware point of view? And the answer is no. It doesn't make any sense from a hardware point of view because that would make it very difficult for us to parallelize within a kernel. So within a kernel, we're pretty much asking programmers to make all the computation parallel, to make no dependencies there. Okay, but you don't want eventually you're going to want things that are dependent on other things. So the question is, when can we put in what we call a barrier so that all computation above the barrier has to finish before any of the computation below the barrier needs to finish? So in this picture, we sort of have a barrier right here. Okay, that we can say, and this is roughly the granularity of a frame, right? So a picture, the whole picture finishes before you start drawing the new one. Here we do the whole computation on a whole time step of this, and then we say, okay, here's a barrier, everybody reaches there, then we swap buffers, okay, then we GL flush or whatever before we start on the next one. So one of the big questions is, what do you do when you're designing the system? It's more convenient for the programmer to have much more frequent synchronization, but that's going to hurt your parallelism and hurt your performance. So they have to sort of balance out performance versus convenience. Great question. Yeah.
Do NVIDIA and say AMD? Do they ever tell you which fragment runs first?
Okay.
Is that a stream processor, or is that always kept secret?
It's not necessarily okay. So we launch this thing. Which one goes first? Okay, so you can figure this out, and this was one group did this for their like undocumented feature project that you're all working on right now. So what they did is they got a utility that turned down the clock on the GPU down to as low as they possibly went. So it was like running at 3 megahertz or something, and then they gave each fragment this really complicated fragment program. Okay, and they just turned on the video and watched. And so what you'd see is these fragments like being drawn in one at a time because it was taking forever and a day to draw each fragment. Okay, so it turned out at least one of them it would go up here. Okay, it would start at the bottom left and then rasterize up this way. So it was cool. It's a great experiment. So they're not going to tell you because it shouldn't matter to you, and they want the freedom to change that underneath. Okay, it turns out it's actually non-deterministic too. So I can run the same program many times, and it's actually going to go in a different order. And I know this is true with some of the GPU computing programs that I've run. I can run it twice, and it would just, for whatever reason, memory conflicts or whatever, it ended up picking things that go in a different order. Okay? The question is, what guarantees does the programming system make to you? And if all these are totally independent, which they should be in your programs, it shouldn't matter to you which one runs first. And the GPU has the power to choose the order in such a way that it thinks is going to be the most efficient. And that's where a lot of the magic happens, right? It can look and say, we'd better start running that guy because he's got a lot of dependencies. We want to send his stuff out to memory. These guys are just doing compute, so we'll wait a little bit for them. That's what it's really good at. Question over there? No. Other questions about this? Okay. This is the biggest thing, like in terms of GPU compute. If you understand this, you're in fine shape. Okay. What we're going to talk about for the next 20 minutes is getting to talk about some algorithms, some things we can do with this. But the really important thing is to understand sort of what the model is here and to understand why the GPU manufacturers have chosen this particular model, right? There's a lot of restrictions in this model. There's a restriction that you can't run these two things shouldn't be dependent on each other. But I hope you realize that by putting in these restrictions, they've made it possible for them to have a very high performance machine that can give you really high, arithmetic bandwidth. Okay. So this is a very old slide. This is sort of showing a, let's see, I believe this is Mark Harris's code. And this is code that he did to do actually a fluid simulation. So this was like he did some cloud stuff. It was really cool. And so he was sort of showing the difference between doing a piece of code in the CPU and calculating, like he did steam kinds of effects. And what it looks like in the CPU and what it looks like in the GPU. And this is C code, and this is CG, which is a graphic shading language. And I said this last time, and I'm going to say it again because it's such an important thing. All right? In GPU computing kinds of things, you write one program, and it runs on every vertex and fragment. You write one program, because it's SPIMD. That's the single program. It's going to run on lots of different things. So if you look at the CPU code here, he's running this over a grid. And so you see him loop over all the elements of the grid. You say loop over I, loop over J. Okay? We go over here, there's none of that. Right? Because he's written one program, and that program runs on everything. Okay? Instead, what you do as the programmer is you define the domain. And you say, I am going to run over a domain of 1,000 by 1,000 elements. Here is the kernel. That kernel is written as if it's going to run on one element. Okay? But the hardware will then launch threads for each of these elements, and everybody's going to know its own local element address and be able to do separate computation and so on. But you only write one program. Okay? There's none of this weird, like, you don't have to do the loop kinds of things. And so that's why this looks a little bit different. Okay, very important point. Does anybody have any questions on this point? Okay, so here's what we have to play with. Here's sort of this is a little bit, we're going to talk a little bit about old Gpgpu stuff in this conversation, but just so you know, what are the pieces of hardware we actually want to compute with? All right, well, we have these parallel processors that we talked about, fragment processors, vertex processors. Okay, we now have a geometry processor if we want. That's new. We have a rasterizer. Okay, so we can use the rasterizer to do interpolation. Right, it'll interpolate addresses if we need to. Like if you run 1,000 by 1,000 and you say this is 0 and this is 1, then the rasterizer is going to figure out that this is at 1/2. Okay, that's sort of built into the rasterizer. Great, cool. Today you should think about that as a rasterizer is something that launches threads. You give it the domain, and it'll figure out how to launch a thread for every element in that domain. So even with modern GPU computing that doesn't use the graphics interface, it's still what the rasterizer does. Okay? You don't get to control that at all. You don't get to write any programs for it. But when you say, I want a domain of 1,000 by 1,000, somewhere 1 million threads are going to get created. Okay? The rasterizer is actually what's making that happen. The rasterizer is what is creating those 1 million threads. Okay, we have a texture unit, so we can go to global memory. Okay, texture is actually read-only memory, but modern memory units can do more complicated things. But if you actually use texture, that ends up being read-only. And then it used to be you could write to texture, and that's the way you'd produce a value. Today it's more flexible than that, but this is there's still write to texture ability in GPUs. Okay, so what do we know about the Vertex processor? This is something that's a little bit of a recap from last time. Fully programmable. works on 4 vectors at a time. The latest NVIDIA chips are scalar, so they only operate on 1 element at a time. Okay, what sort of things can it do? Can it do vertex texture fetch? Can it scatter and so on? Again, this is kind of historical information, so I'm not going through it in too much detail. Fragment is historically where most processing has happened. Okay? Most Gpgpu has been done in the fragment processor, and the reason is because there's more fragment processors on a chip than there are vertex processors, because each triangle ends up generating many fragments. So you need to have more fragment processors than vertex processors. Okay? So again, historically, this is 4 vectors. Now it's scalar. Historically, fragment processors were gather but not scatter. But now we have native scatter, where fragment processors can write back to just about anything. Okay? So the graph that I showed at the beginning with the big curve, okay, the last couple points are ones where you're using general purpose interface. But all the early points are ones where what they did is they wrote a fragment program to just do math. Okay? This is where most of the math is in the chip. And this is the part, this processor is where you would do all your Gpgpu stuff. Okay, so it used to be we had these separate vertex and fragment processors. And you would have to target some code for one, some code for the other. And so what the latest chips are is they say, well, you know, why would we build 2 different kinds of processors? What we're instead going to do is have one pool of processors, and it can be used for either one. And that's been made possible because the instruction sets have really converged here. Okay, cool. So the outcome is this, what we call a unified processor. So there's only one kind of processor core here, and now there's a pool of these processors that can be used for any of the programmable tasks in the system. Right? So what you want to think about is these are SIMD, fully programmable, and you want to think of each of these thread processors within a unified processor as processing 1 thread each. And on the GPU, at any given time, you're going to have thousands of threads active at a time. At least if you're keeping it busy, there's thousands of threads active. Right? There's probably hundreds of threads that are actually doing something, but there's a bunch of threads that are just waiting to start, and there's a bunch of threads that are waiting for memory to come back. And you need all these threads because every time you stall, you need another thread to come in and take its place. So this is what the hardware is really good at. It's really, really fast at switching between threads. And it's very different than the CPU. CPU is going to take hundreds of thousands of cycles to switch from one thread to another. Context switch is expensive. Okay? But on the GPU, it's a zero-cost context switch. It is free to switch from one thread to another. And threads are very lightweight, and they've done lots of architectural cool things that hopefully John Nichols can tell you about to make this possible. But it's very important that they switch from one to the other very quickly. And it's so that they can do this latency hiding stuff. So these modern unified processors, they can do both gather and scatter. The other thing that NVIDIA does in their chips that's kind of cool is, well, if I am a thread and I have another thread right next to me and we actually want to share data, okay, I want to write a piece of data so he can use it, okay? Historical GPGPU, that's really hard. Like what I have to do is write back to main memory and then do like a flush of everything, like finish my whole frame and start a new frame, and then I can read that value in the next thing. That's really expensive. And it's a long way to go if you've got 2 threads that are right next to each other. So we'll talk about this a lot more on Thursday. But NVIDIA says, all right, we're going to organize these threads that we launch into blocks. Okay, and we're going to have a little block of threads with a couple hundred threads in it. And that block of threads is going to have a little piece of memory in it that all threads can access together. A little piece of shared memory. Okay, and it's called shared memory. And so it's not very big. Okay, it's like 16 kilobytes. But all these threads get to share from it. So instead of having to go out to main memory to share and having to do a big flush and flush the entire pipeline, instead now we can have this little shared memory that a few threads get to talk through. And it turns out that's very useful for lots of operations.
So are SIMD instructions just considered a special case of SIMD where it's just broken up into different threads? I mean, are there any actual SIMD instructions?
Well, the SIMD instruction is you have many thread processors and one control unit. And if the control unit sends an instruction that everybody ends up doing and nobody's masked off, that's SIMD.
But it's still SIMD generally. Right. Yeah.
Cool. Nice Venn diagram for today. Okay, other questions about this? Okay, we will look at the hardware in more detail on Thursday. Okay, so skip that. Do want to talk about the memory hierarchy just a little bit. So you're writing a GPU program, right? What do you actually get to access? Okay, where does data live? All right, so CPU, you kind of know about this. You know about your registers. You know about your caches. You have main memory. Okay, GPUs are a little bit different memory hierarchy here. So you're writing a GPU program. Every thread has its own set of registers, right? Just like a CPU program. Okay. There's also this issue of constant registers. So you can have a set of registers that you can't change, at least once you initialize them, but all threads get to read those constant registers. Okay? We saw the same thing in our Vertex and Fragment programs on Thursday. Remember, we had a bunch of constant registers that we used for things like the transformation matrices and the lighting parameters and material and so on. Okay? Those are things you set once that are part of GL state that you aren't going to change again, but then everybody wants to be able to read them. So one thing you can do in a general purpose program as well is you can have constant registers. Okay? There are some caches. You don't know a lot of details about them. There's both texture caches that are used for in the texture pipeline and these shared memory kind of caches that are used for small blocks of threads. And then you have this main memory, video memory, DRAM, that's actually on your GPU board. Okay? Now, each GPU thread can read from this, read and write from this, read and write from this, but if it wants to talk to anything over on this side, the CPU has to get involved. Okay? You can't write a GPU program that goes and reads from CPU memory. Instead, the CPU has to say, okay, I'm going to move a block of memory over there. Okay, now I'm going to kick off a GPU program, and the GPU program can read from that copy that's in GPU memory, but that's all it can do. Okay, so there's sort of a limited scope that a GPU can actually read from. Okay. So, okay, memory model, more restricted. Okay, so I guess one point I want to make here is that what we're essentially doing when we do computing in general is that we create this giant data structure of some kind, okay, this vague bubble of data, and then we operate on it. Okay, so that data structure could be a giant grid of initial positions, and we operate on it and create the next time step. It could be a giant, tree or graph, and we operate on that. I mean, there's basically compute operates on a big chunk of data. What is that chunk of data? Okay, so what do we want to do with that data structure? Well, we want to be able to create it. We want to be able to update it. We want to be able to access it. Okay, we want to be able to change individual items in it. There's lots of different things that we can do. So what GPU computing usually does is that the CPU builds up some sort of data structure. Okay, and it's good at that. And then it takes this data structure and it copies it over to the GPU. And what the GPU is really good at doing is accessing that data structure because it can do so in parallel. It's got lots of threads, and all of them can reach into the data structure and grab data, and there's no conflicts going on there. Okay, so it's efficient at that. And so sort of one of the big questions we're looking at is, really, is this the way that we want to think about things? Do we want to always divide up like, okay, the throughput-oriented processors are doing the accessing, the latency-oriented processors are doing the building? Is that really the right thing to do? We're looking at figuring out how GPUs can do things that they're not historically good at. Could GPUs construct these data structures? Okay, it's hard to do in parallel. It's a real research challenge. One thing that PlayStation 3 developers found, so if you look at the PlayStation 3 architecture, it turns out the bandwidth between the CPU and the GPU there is really high. Okay? Much higher than you would get off PCI Express, and certainly much higher 3 years ago when the thing shipped. So what the developers found is that, okay, well, when you eliminate that bottleneck by making that thing really fast, they did much more ping-ponging between the processors. They found that if they had higher bandwidth between their CPU and their GPU, they looked at data structures very differently. So today, in a lot of GPU computing, what you're really trying to do is minimize the amount of traffic across that bus because the bus is so slow. But if that bus was really fast, you might move it often because you really want to do the right computation on the right processor, on sort of its native processor. And so we're not sure what that looks like going forward. Is this bus going to get faster and faster, and thus we're going to be able to change the way we think about these things? Or is it going to continue to be far apart, in which case sometimes you're going to have to do the wrong thing on the wrong processor because it's so expensive to send it back and forth? That's just sort of a meta topic here. But in general, this is the big picture I want you to think about is which things are the CPU good at and which things are the GPU good at, and how do we structure things so that we're keeping them both busy all the time and we're not spending all of our time shuffling data back and forth. Okay. Sort of went over that. Okay, so I got 10 minutes. What I'm going to talk about for 10 minutes, and then I'll stop, and I don't think I'm going to get through all this, is, okay, we've got this big picture here. Okay, we know sort of how GPU computing works. We know the big picture of how we structure a GPU program, what sort of things a GPU can do. Okay, and what we're going to look at is looking at different kernels, different building blocks for how we do computation. Okay, so we're going to start off with very simple tasks and say, okay, how do these map to the GPU? But then we're going to have some things that end up being a little bit more complicated. And how do we map those to the GPU? How do we do these things that don't immediately look parallel? Okay, so this is sort of my motivating application. And I totally made it up, so don't take it seriously. What we're going to have is a big sort of terrain map. Okay, and it's going to be on a grid. And what I'm recording is a height at each piece of the grid. Okay? And so what I want to figure out is how bumpy is that grid. I'm going to take in, a million grids. I'm going to say, okay, what's the bumpiest piece of land out there? Okay, and this is the way that I'm going to figure that out. I'm going to look at all the elements in this grid. Okay? And at each element, I'm going to look at the element compared to all of its neighbors. And if the element is right at the average of where its neighbors are, then it's kind of a flat portion of the grid. If all of its neighbors here and it's way up here, then that's a really bumpy piece of the grid. Okay, so I'm going to do that comparison. I'm going to take the difference between the average, where it should be and where it actually is, and I'm going to square that. And then what I'm going to do is I'm going to add up all those differences across the entire grid. Okay, so every element is going to compute this shared difference, and then I have to add them all up together. Okay, but there's going to be a lot of places on the grid that are flat, so I don't want to add up a bunch of zeros. Okay, that's a waste of time. Instead, what I'm going to do is only sum up the differences that are not zero, and that's going to give me the bumpiness of this particular grid. Everybody cool on the application here? Okay, here's what it looks like in code. Okay. At all samples, I'm going to calculate the average value of my neighbors. Okay, grab all my neighbors, multiply them by 1/4. I'm then going to take my value, subtract off my neighbor average value, and square that difference. Start off with a scalar value. So that's all in parallel, right? Perfectly parallel. It's really nice. Start off with a scalar value on result. And then for every place where this difference is not zero, I'm going to add that to result. Okay, so you probably look and you say, that's pretty parallel. That's a little harder. So we're going to start off looking at these problems. Okay, so first I'm going to look at this. So this is nice. So basically what I'm going to do is I'm going to declare a domain that's over this entire grid. Okay, 1,000 by 1,000, or however big I want to make it. And I'm going to spawn a thread at each one of those grid locations. So at every xy, I'm going to spawn a thread. And at each of those xy's, I'm going to want to compute this. The nice part about this particular computation is that it only has two inputs. Okay? It has my value and the value of my neighbors, and I'm not even looking at how I get the value of my neighbors yet. But it's an entirely local computation. It is completely data parallel. Right? If I had 1 million processors, I could calculate 1 million of these things at the same time. There's no dependencies. I've structured this problem in such a way that there aren't dependencies. So that's kind of cool. So we call this operation map. So we take an array or a stream and a function. Okay, these are sort of our inputs. And the operation map takes the stream and takes the function and applies that function to every element in the map. Okay, so I've declared this grid. I'm going to want to do compute. I'm going to do the same thing on every element of the grid. Okay, this maps very nicely to a graphics processor, so it's real easy. So in the graphics world, you can say, well, A is a texture. Okay, and so you've got this giant texture with all these values in it. You render over that texture. It's going to create a fragment for every texel in that texture. You're going to do your computation. General purpose, you say, okay, this array declares a big computation domain or a stream. Each element is going to be an element in that domain. Okay? You have a pixel shader or a kernel that'll actually implement the map function. Every element in that is going to go out and read its value and the averaged value of its neighbors. Okay? In graphics, you do this by drawing a giant quad. And in general purpose, you just declare the size of this domain. Okay? So this should be very straightforward. Okay? Any questions about the way this works? Okay? This is easy, and the GPU should totally rock at this because you've got perfect data parallelism there. Okay. So a little bit more complicated is this averaging problem. All right? So now, this is kind of interesting. My computation is dependent on the values of each of my neighbors. Right? I'm going to want the value of this neighbor, this neighbor, this neighbor, and this neighbor. Okay? So, is this data parallel or not? Is this perfectly data parallel or no? Are there any dependencies here? Do I have to go in any particular order? Okay? So why not? How can I look at this code and know that this is parallel?
Because the value array doesn't change.
That's great. That's exactly what I wanted to hear. Value is read-only here. Right? Never change value. So when I start this computation, value is set. Okay? And I'm going to compute neighbors, but everybody's going to compute its own neighbor. It doesn't matter which order I go, and there's no conflicts between those computations. Okay? This is entirely read-only, and because it's entirely read-only, okay, it's totally data parallel. That's perfect. Thank you. Great segue. Okay. So everybody cool with what I'm doing here? Okay. So here, maybe I have value, maybe I have this neighbors in 2 registers. Here, though, I'm probably going to have to go out and get somebody else's value. I'm going to have to go out to global memory, okay, go out to my DRAM, and pick these things up. Okay? So what I've done here is an operation that I call gather. Okay? Over here is gather, where I reach out and grab information from my neighbors or from global memory that's associated with my neighbor. Okay? I could have also expressed this problem in terms of scatter. Okay? Where what I do is I push my information to each of my neighbors. Okay? And that would have worked fine. I could write it that way. So where I push to my neighbor, and this neighbor, and this neighbor, and this neighbor, and 4 people push to him, and then he adds up all those values, divides by 4, and he's done. Okay? Instead, I chose to express this as a gather rather than a scatter. Historically, that's the right thing to do because early GPUs didn't support scatter. Today, GPUs support scatter, but it's still beneficial to do gather in this circumstance, and how come?
The gather is from a texture memory, so it's quicker than scattering to global memory.
So that may, well, I don't know if you can make that promise with today's GPUs, but it's not the answer I'm looking for. It might be correct on today's GPUs. Let's just say we implemented it all in general purpose memory, though. No texture at all.
Is it because you can get the values when you want them and not have to wait for the scatter to arrive?
Well, you hope that in a throughput-oriented machine, okay, you hope in a throughput-oriented machine it shouldn't matter. That you might be waiting or you might not, but it's going to be able to keep the machine busy.
With the scatter, wouldn't you have right order dependencies?
So your issue here is that now that if we do a scatter, if we say I'm going to push this value, push this value, push this value, push this value, now we've sort of introduced some data dependencies. Right? We've got to push, this guy is going to receive 4 values. He's got to get them in the right order and add them up and so on. Okay? You could maybe express it in such a way where that wasn't an issue. You could open up 4 slots and everybody writes into his own slot, and maybe there aren't dependencies. But when you do the write, the global write, you have to worry a lot more about ordering than you do with a global read. Okay? Global read is something that's perfectly parallel. So it's useful to be able to look at methods to convert from gather to scatter. And this is sort of my last 2 slides here, so let me explain. For instance, we're doing a spring simulation. Okay? And so we calculate the force on this spring, and we take, this spring says, what I want to do is add here and add here the force of my spring. We've computed that. So that's scatter, right? I'm taking my value and I'm writing it to my neighbors. Okay? So there's maybe some ordering issues with that. So I have to think about my problem in a different way. And instead of iterating over all the springs and pushing my force, okay, I can think about computing the force, but then iterate over all my masses and fetch my force. Okay, so what I've done is I'm now iterating over masses instead of springs, and when I iterate over masses, it becomes a gather problem rather than a scatter problem. Okay? In general, gather is a little bit preferred on today's GPUs because you have to deal with all these ordering constraints when you have scatter kind of computation. And so there's some nice tricks to be able to turn things that look like scatter into something that looks like gather. Okay, when we come back on Thursday, we'll do the next two kernels and then talk about NVIDIA's implementation of this.